Okay, so hello guys. In today's video, I'm gonna be giving an introduction to neural networks. So in case you weren't familiar with neural networks, in case you know classical machine learning like linear regression and logistic regression, but you're not familiar with neural networks, or you don't know any machine learning algorithms, but you wanna know about neural networks directly, this video is right for you. Also, I'm making this video because a lot of people complained that my course on advanced deep learning that contains LLMs and generative models is a bit advanced and they don't know the prerequisites. So this video will serve like a prerequisite to my advanced deep learning course. So in case you're not familiar with deep learning at all, you can watch that course. At the same time, in case you just wanna know what neural networks are, this video will be right for you. So in today's video, we're gonna be explaining what neural networks are. We're gonna give a small notebook, a numeric example, and speak also about how the learning happens in neural networks. So let's get right into it. So before we start, let's talk about gradient descent, which is the algorithm that neural networks updates its weights using. Basically here we're talking about how learning happens. So how does a neural network learns? So when we say learning, what do we mean? Usually in machine learning algorithms, we're trying to find a function f of x such that because we have training data, all right? We have data. And in our data, we have x and we have labels y. So we're trying to find f of x, which is an approximation of the actual function f of x, such that the predictions of f, so the outputs of this function f hat, are as close as possible to our labels in the data. So I'm gonna say it again. We're trying to approximate a function f of x such that in our data, in our training data, for every x, this function that we found gets labels as close as possible. Now, it doesn't get it right 100%. We get it up to a certain accuracy, but we try to approximate x as much as we can. All right. So, let's take a small numeric example to understand how gradient descent operates. So let's say we have this data over here. So we have when x is 0, y is 0, when x is 1, y is 2, when x is 2, y is 4, and when x is 3, y is 6. Alright, what does this mean? This means that, if we plotted x against y, we will get a curve that looks like this. It's y equal to x, basically. We humans can see it. This is a very simple linear regression problem. Now, okay, so we see that y equal to x. But, this is the actual f of x. This is the actual f of x. We will try to approximate it. So the way we try to approximate it is with y is equal to ax, and we're trying to find a over here. So we're trying to find this a that approximates this with the highest accuracy possible. So how do we find the a? So it's very simple. We do multiple iterations. At every iteration, we have our training data. We use our f so far. So we found an approximation of f so far. Let's call it f hat. So we use our f hat. We test it on training data. We get the output, and then we calculate the error, which is the prediction of f against the actual f. So let's try a very quick example to see how it goes. So let's say we initialize a to 0. So we have y is equal to 0x. What does this mean? Let's draw a very quick table. So x, y is the actual y, and now y hat, which is our prediction, and the error. Now let's say we're testing the error with the absolute difference between y and y hat. Okay, so here we have 0, 1, 2, 3. Here we have 0, 2, 4, 6. And because y is equal to 0x, 0 multiplied by anything is 0, so here we have 0, 0, 0, 0. When we calculate the absolute difference between this column and this column, we'll get 0, 2, 4, 6. So if we calculate the average of the error, which is the addition of all of these, over 4, we will get 12 over 4, which is 3. So the average of the error, so the error so far is equal to 3, which is quite high. How gradient descent operates is that you update your parameter set to 0. Is a new value would be the old value, this is the old value, minus the learning rate. Let's say we set the learning rate to 0.25. And the higher the learning rate, the quicker the learning happens. However, usually you test to find what is the best value for the learning rate. So the new value of the parameter is the old value minus the learning rate multiplied by the change of the error with respect to the parameter. So let's say, so in our example, y is equal to 2x. The actual function, let me draw it in blue, it's this one. And let me draw in red our function so far. Our function so far is y is equal to 0x. When we calculated the error, we got 3. We will update our line. Let's say we update it. Let me draw it again in red. Now we get this y hat. So y hat was here. Now it's here. We will do it. Let's say now we have y is equal to 0.5x. We will do the same operation again. However, this time, let me delete this column. Because now y is equal to 0.5x, here we will have 0, 0.5, 1, and 1.5. And we will calculate the new accuracy errors. We will get 0, 1.5, 3, and 4.5. Now, when we sum these up, we will get 9. 9 divided by 4 is 2.25. So now our error is the summation of y minus y hat over 4. Now the error is 2.25. So it dropped. It used to be 3, now it's 2.25. So we update the parameter we're trying to find, a, as follow. A is equal to the a new is equal to a old minus the learning rate, which we chose as 0.25, multiplied by the change of error with respect to what? With respect to a. Change of error with respect to a. So the old a is in this case now at 0.5, because now we have y equal to 0.5x, minus 0.5 multiplied by what? It's multiplied by the change of error. The error used to be 3, now it is 2.25, over the change in a. A used to be, when the error was 3, a used to be, it used to be 0, minus, now it is 0.5. So we will get 0.5 minus 0.25 multiplied by 0.75 over minus 0.5, which is 1.5. So we will get 0.5 minus, we calculate this value over here, we will get 6, which is quite high, so we will get minus 4.5. Now we got this very big amount mainly 0.25 multiplied by 1.5, it's not 6. Why did I? So it's 0.375. Okay, so it's 0.375, so we will get 0.125. So as you can see, like we will keep like doing this operation and like moving the line over here. So initially it was here, it was here, then it will become 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 here. Suddenly it's gonna exceed it, and then finally it'll become directly above it. It's what we hope will happen. So that's how usually gradient descent operates. So the function keeps alternating above the actual one. So I hope it's clear. So in a neural network, like the one we have over here, we have many weights. So here we have W1, W2, W3, and so on. So every line here is a weight. Also we have many biases. So here, because we have a node, we have what's called a bias, which is added to the summation at this particular node. So usually to calculate the value at a node, we do it using this formula over here. We sum up all the incoming weights. So summation of Wi multiplied by the input. So the input may be the actual input, because here we have many inputs, or it may be the previous node, because like this node over here, it sees the node before it. I hope it's clear. So we have many inputs, and the way we would do it is we would sum up the weights of the nodes multiplied by the inputs before it, and then we would add the bias. Then we will apply our activation function. Now the activation function is a function that would add nonlinearity. So if you want nonlinearity in your neural network, you need to have an activation function. And I put some of the activation functions, the most common ones over here. We'll go over them in a bit. But let's say you have this activation function over here. It's 1 if the summation of Wx plus b is positive, else it's 0. So this is its curve. If it's a negative number, you will get 0. If it's a positive number, you will get 1. So the idea is you would sum up W1x1 plus W2x2 plus W3x3 plus W4x4. Then you would add the bias. Let's say the bias is 2, so you would add 2. And then you would check, is this value positive? If it's positive, you will get 1. If it's negative, you will get 0. And that's the idea. So let's say this is called I1. So to calculate I1, you do W1 multiplied by input 1 plus W2 multiplied by input 2 plus and so on, Wn multiplied by input n. You would add the bias of I1. Let's say it's 2. You would check, is it positive? If it's positive, you will get the value 1 here, else you would get 0. You would do the same for I2. Let's say you get 0. Let's say then you get 1. Let's say here you get 0. And then to calculate H2, you do the same operation. Here you have a new weight. Let's say here you have W30. So W30 multiplied by I1 plus W31 multiplied by I2 plus blah blah blah. Then you would add the bias of H2. Then you would check, is it you would apply your activation function and get the value. You keep doing it until layer n. You calculate the value at every node. Then for the output, for every output, so here let's say you have W100, you would do W100 multiplied by IN plus W101 multiplied by IN plus 1, and so on. Then you would add the bias, and at the end you would get your output vector. Now, at a later on in the video, I have a numeric example that will make it much clearer, but this is a basic idea of what neural networks are. Now here I have some of the most common activation functions. So we have the step function. If z is negative, you would get 0. If z is positive, you would get 1. So it would look like this. I have the signum function. It looks like this over here. It's -1 if negative. At the 0 it's 0, and then it's 1. So it looks like z. The linear function f of x is equal to x. You basically take the value. And usually we use this one at the output. We have the ReLU, which is usually used at the middle layers. If it's negative, you get 0. If it's positive, you take the value like it is. We have the sigmoid. It's exponential x over 1 plus x. And we have the tangent hyperbolic, exponential z minus exponential minus z over exponential z plus exponential minus z. Now, usually, how do we pick our activation function? Because it's not a learnable parameter. We usually test it out. However, we usually look at previous machine learning papers on this particular topic, and we see what they picked. However, usually at the output you either use a linear function or a tangent hyperbolic, and usually like in the middle layers you use a ReLU or a step, I don't know. Okay, so it depends. So what's learnable and what's not learnable? So in neural networks you have many parameters. Like in linear regression, like we just saw in our example in y equal 2x, we only had this parameter to learn. So we had one parameter. However, here, as you can see, you have many parameters to learn. So we learn all the W's, so all the weights, and we learn all the biases. And the way we learn them is we initialize them to 0 or to a certain value, and we update here. Let's say theta 0 is every weight, and theta 1 is every bias. We update every weight and every bias by the change of the loss with respect to this weight or to this bias, and usually the code does it for us. So let's look at this tiny numeric like these tiny two examples I put over here. So first we initialize, we try to turn on the GPU. Don't forget to change runtime type to GPU to make it run in parallel. Here I'm doing the XOR operation, and in case you didn't know, the XOR, if you have the same, if you have 0 and 0, they give 0. So 0 and 0 gives 0, 0 and 1 gives 1, 1 and 0 gives 1, and 1 and 1 gives 0. So very easy. So this is the truth table. So here we have x1, x2, and y. Here y is equal to x1 XOR, I'm not sure about the symbol, I think it looks like this, x1 XOR x2, 0 and 0. So here, as I just said, they have to be different to give 1. So 0 and 0, it gives 0. 1 and 1, it also gives 0. 0 and 1 gives 1, and 1 and 0 gives 0. So we're trying to make a neural network that takes two inputs, x1 and x2, and finds at the output the XOR between them to match our data. So we need a data set. So how I do it is that I would put the value of, so here I made the table, 0 and 0 it gave 0, 0 and 1 gives 1, 1 and 0 gives 1, and 1 and 1 gives 0, and I use the dot repeat function, and basically it repeats this this value. So here I make a vector of 256 values, 256 rows and 1 column, having the values of x train and y train. And this is how I make my data set. And then I use tensor data set. I give it the x train and y train, and then I use the data loader, which we imported from torch.utils.data, and we give a batch size. So that's it. And you put the x and y to device, because we're doing parallelization to have a faster training. Now the next step is you need to make your neural network. So you specify a class. This class has to inherit from nn.module, and nn.module is basically the neural networks module. Usually when you want to make a neural network, you make your neural network inherit from neural network.module. So first you have to make the init function. You call super.init to initialize the neural network.module, and then we put, so here I made in my example, I made a very simple neural network. So we have x1 and x2, the two inputs, one hidden layer, this is the hidden layer, I1 and I2, and one output. And in the so because we went from 2 to 2, and I put a linear layer in the middle. What linear layer means that it's basically y equal x, okay? And then the activation function is the tangent hyperbolic in the middle. And at the end, because we had two inputs and we have one outputs, I put nn.linear. And in the forward, basically, you call self.fc2 on the activation of self.fc1. So we return self.fc2 on the self.activation of self.fc1. It's very easy. And then I printed the number of parameters, which is the sum of p dot numal for p in model dot parameters. We got 9 parameters, which is the case over here. Here we make our training loop. We specify how many epochs, so how many iterations we're doing. At every iteration, we load from the data loader the x and the y. We calculate the output of our model, and we calculate the loss between the logits and the actual y. And then we call opt.zeroGrad, and opt is basically our optimizer. I'm gonna make a separate video on optimizers. However, optimizers basically they do the gradient update. We call loss.backwards to do the gradient descent, and opt.step to advance. And then we add the, because we're calculating the average of the loss, we add the loss.item on the total, and we print it at every step. So as you can see, in every 50 epochs, the loss is going down. It used to be 0.008, it becomes 0.002, so it dropped by 75%. No, by 400%, sorry. And then it becomes 0.00075, and so on. At the end, I printed the weights and the biases. So here we have our prediction and the true for an example. When 0, we got 0, 1 is 1, 1 is 1, 0 and 0, which is the case, which is great. So I had to change where I was sitting because my laptop ran out of battery. So again, so we do model.eval to evaluate our model. When x is 0 and when both are 0, we would get 0, 0 and 1 we would get 1, 1 and 0 we would get 1, and 0 and 1 and 1 we would get 0, which is the true. So our model has a very high accuracy. Now here I printed the weights, and here I drew the network, like the final network. So we got x1, we got x2. To calculate I1, the first hidden layer, we do I1 is equal to summation w, so it's the activation function, which is the tangent hyperbolic, of w1 x1 plus w, so I gave them a different name, but like the name associated with plus w2 x2 plus B1. So in this case, here I gave them a different name. So here we have the W1 is here, W2 is here. So we do 5.7 multiplied by x1 minus 5.5 multiplied by x2. So it's the activation function, which is the tangent hyperbolic of 5.7 multiplied by x1 minus 5 point how much? 5 multiplied by x2 plus b1. B1, the network found it to be 2.61, so plus 2.61. So I calculated this quantity over here, because for 0 0 so for 0 for I calculated it for 0 1. So for 0 1 minus 5.7 multiplied by 0 minus 5.5 multiplied by 1, you get minus 5.5. Then I add the bias, which is 2.61, we get minus 2.89. I did the tangent hyperbolic of minus 2.89, I got around minus 1, I got minus 0.999. I did the same for I2. So I2 is W3x1. I2 is the activation function of, so I2 is the same. So it's the activation function, which is the tangent hyperbolic of W3x1 plus W4x2 plus B2. I calculated the value over here. So we get 0 multiplied by minus 5.9 plus 6.35 multiplied by 1, and I did the tangent hyperbole, plus we add the bias, which is 2.67, we get 9.02. I did the tangent hyperbolic, I got around 1. And finally, for the output layer, for the output, we have W5 multiplied by I1. I1 is the hidden layer previously, plus W6 multiplied by I2. I2 is the second value we calculated over here of the second node, plus B3. Okay, and in my code over here, I didn't have so I only have so B1 is actually B1 and B2. B1 is a vector, so actually we have B1 and B2, and B3 is actually B2 over here, so plus 11. Anyway, so W5 over here is minus 12. So as you can see, minus 12 multiplied by so here we have O1 is equal to around minus 12 multiplied by minus 1 plus 12, I think. Yeah, no, another minus 12. So we have another minus 12 multiplied by plus 1. I guess they would around cancel each other. Plus we add the bias of around 11. We would get a number around 11. And yeah, that's it. So we do it, that's how we calculate it at every time. We calculate I1 and I2, then we would do W5 multiplied by I1 plus W6 multiplied by I2, and then we would add the bias. And basically how the network found these numbers over here, it did gradient descent. So it just did gradient descent, as easy as that. So it initialized the weights, and at every epoch it calculated the loss and updated every weight by using the formula of the weight in U is equal to the old value of this particular weight minus the learning rate, which is usually around 0.1, multiplied by the change of the loss function, which expresses the error with respect to this particular weight. So the change with respect to this particular weight, and that's how you update. And this is how a neural network would learn. Here in my, I put another numeric example of 16-bit parity. So if we want to know if it's even or odd, so if it's 1, it's odd, and if it's not 1, it would be 0. So here we have xb and yb. Here I made a function make parity data set. It takes a number of samples and number of bits, which should be 16. xb is a random int of between 0, so between 0 and 2, so we would get 0 and 1. And number of samples and number of bits, because here we would have like a big matrix. Number of bits is 16. Number of samples, let's say we had like 500 samples, so we would have 500 rows. Every row is 16 column, and the 16 column are every particular x. So like one column may be 1 1 0 0 1 1 0 0, and then 4 zeros, and then 4 ones. This is of even parity because we have an even number of ones. This is one sample, and we do it for all the number of samples, and this is our xb. So xb would have sample 2, sample 3. This is sample 1, by the way. And this is how we did it using this function. And yb is simply we count the number of we sum up the numbers and we do modulo 2. That's it. Okay, and this is how we can know if we have an even number of ones or an odd number of ones. So we make x train and y train using make parity. We give that we want 60,000 samples. Then we make our x val and y val. And by the way, every sample is sampled uniformly because we use the rand_int function. And then we make our train data loader, our validation data loader using the data loader function. And we give a batch size. Here I gave a batch size of 256. And finally I printed xtrain.shape and ytrain.shape. So we have 16 columns for xtrain because we have 16 numbers, and y is simply 0 or 1. Is it even or is it odd? Now for our neural network here we had a bigger neural network. So we had initially, we take 16 bits and then we go to 256. We apply tangent hyperbolic. Then we go from 256 to 256. Then we apply tangent hyperbolic. Then we go from 256 to 128. Then we apply tangent hyperbolic. Then we go 128 to 1. Let me draw it over here. So initially we have 16. So here we have x1 till x16. Here we have, in the first layer, let me call it h1. Here we have 256. So here we have h1 comma 256, and here we have h1 comma 1, and we would basically connect x1 to every node here because here we have a fully connected layer. Same for x2, same for x16, and here we have 256 nodes. And the activation function here is tangent hyperbolic, so you do summation xi bi plus summation wi xi plus bi, then you apply tangent hyperbolic. In the second hidden layer, here we also have 256 numbers. So here we have h2 comma 1 till h2 till the node h2 comma 256, and also we do the same operation. So we do exactly the same operation. And then we have a third hidden layer of 128. So here we have h3 comma 1 till h3 comma 128, and we also connect every number to every number. And finally at the output layer we only have one node. So here they're all connected to this particular node. So you may ask what's the number of parameters, and here I printed it, and yeah, that's it. So we go from 16 to 256, then from 256 to 256. Oh, I don't have we don't have a middle hidden layer. So here we don't have H2. We go from H1 so this is actually H2. So this is connected to this, okay? And if you want to calculate the number of parameters, basically we went from 16, which is 2 power 4, to 256, which is 2 power 8, if I'm not mistaken. And then we went from 256 to 128, which is 2 power 7. And then finally we went to 2 power 0. If we multiply all these numbers, we would get 2 power 4 by 2 power 8, 2 power 12, plus 2 power 7. We would get around 2 power 19. If I'm not mistaken in my mathematics somewhere here. So 16 is 2 power 4, 256 is 2 power 8. Okay, anyway, so I printed the number of parameters, I made the model, and for the loss function I didn't use like the loss function over there. Here I use a binary cross entropy. Now let's like see it. So this is a binary cross entropy. It's basically this function over here. Let me copy it. So let me copy it again. So it's basically this is a bad example. Okay, so basically it's minus log p if y is equal to 1, or so you have two cases. Either your label is, let me copy it. If your label y is 1, you do minus log p, and if it's 0, it's minus log 1 minus p. And p is your output probability, because we're predicting probabilities. And in our example over here, at the end we're doing a linear layer, but before it we're doing a tangent hyperbolic. So basically we're getting probabilities. Now, to get the accuracy, we get the probability. If it's bigger than 0.5, we're taking it as 1. If it's less than 0.5, we're taking it as 0. So we check, is the prediction, which is 0 or 1, is equal to the actual y, to the label? If it is, we take 1. If it's not, we take 0. If it is equal, we take 1, else we take 0, and we do the mean, and that's it. And here we have our training loop, just like the training loop before. Here we have our validation loop, just like the validation loop before. Because we're summing up the training loss, we divide by the length of the training data loader, because we're calculating the average of the training loss. Same for validation. And here I printed at every epoch how much the training loss and validation loss is. So let's just look at validation is just for generalization. Training is how much we memorize our training data. So let's just look at the training. It started at 0.69. As you can see, it's dropping. So here it becomes 0.67. At epoch 14, as you can see, we have a major update, because it's become 0.2419. At epoch 30, it's become 0.062. It continues to drop. At epoch 87, it's 0.017. Suddenly it becomes, at the end, 0.0011. So the accuracy is quite high. Here I printed the test accuracy, and here I printed some examples. So here we have 1 1 1 1 1 1, so 1. So we have 7 ones, which is an odd number of ones. It should be 1, it predicts 1. And here's the actual probability that was predicted. So it's 0.999, and if it's greater than 0.5, we're taking it as 1. Here's the second example. It should be 1, it predicts 1. So the model performs quite well. And so I drew it over here. Again, I drew the network. Where did I draw it? So let me give like a... So we have our X, which is of size 16. We go to a first hidden layer, H1 of size 256, then to a second one of size 128, and finally we predict the output probability, O1 of size 1. We connect every node here to every node here, same here, same here, and we add the bias and we do the activation function. Here we have the tangent hyperbolic here as well. However, at the end we have a y equal x, the linear normal layer. And again, here are all the activation functions. Usually we use tangent hyperbolic a lot, we use linear a lot, and we use the ReLU a lot. So that's it for today's video, guys. Again, we have weights, we have biases that are learned by the network using gradient descent. The size of the network, how many hidden layers we have, the activation functions. We usually check the task, we check previous machine learning papers, we do like they did, and we copy them. I advise you to try to implement the labs that I will attach to the description here on your own, and you have the solution over here. If you enjoyed the video, don't forget to put a thumbs up, and if you have any questions, feel free to leave them in the comments or to message me on my private LinkedIn that I will also attach in the description. I will also attach in the description a video on gradient descent that's much more emphasis on gradient descent if you wanna know more information about it. Also, I will attach a video on activation functions that I also advise you to watch. And if you understand this video, you're ready to watch my playlist, watch a video on UNet, which is basic computer vision, and then on generative AI with diffusion and with variational autoencoders, and to watch the LLM video, but before where I implemented ChatGPT from scratch. That's it, guys. I hope you have a lovely day. See you. Bye.